Good afternoon, Professor.
Good afternoon. Thank you. Good afternoon. Good afternoon. I think that was Caroline. Good afternoon. David. Oh, there's more. David K.
Good afternoon.
That was Caroline. I'm sorry. Okay. Good afternoon. Good afternoon. And the first person who said good afternoon, I'm sorry. I thought it was, who was it? I don't even know who it was, but good afternoon. Sorry. Not that it's a thing, but it is kind of a thing. Yes. Okay. So good afternoon, person who I didn't see the Greek square around the square. Good afternoon, Caroline. Good afternoon. I'm in the chat now, and you can identify yourself if you want, but good afternoon, Kevin, Lynn. Good afternoon, Felicia. Good afternoon, Jamalette. Good afternoon, Sophia. Good afternoon, Alicia. Hi, Christina. Good afternoon, Chloe. Good afternoon, Caitlin. There she is, not meaning Caitlin, but Amanda. Awesome. It was, and good afternoon, but it was direct chat. Okay. Thank you, direct chat person, for identity. I totally appreciate it. I will remember that forever. And I know, and we have a meeting tomorrow, I think, right? Direct. Okay. Anyway, confirming tomorrow. Yes. And good after, but thank you. I hope you're hearing me. Good afternoon, Amanda. And there's more people coming, and I'm yelling for no reason to overcompensate. Good afternoon. Wait, that was good afternoon, Sam. Good afternoon, David P. Good afternoon, David K. And there's still a Savannah. Okay. And good afternoon, Elda. And good afternoon, Amy C. And good afternoon. Whoa, Team Wahoo. I like the Team Wahoo. That's awesome. Oh, hello, Elda. Thank you. I mean, hello. And I know you've been here since 1967, which was a good year for grapes. Okay. Who else did I miss? I think that's everyone. Okay, cool. Oh, and see, you guys did. And again, really quickly, okay, we have things to do, but I just do want to say again, I'm starting to meet some of you in the halls recently, which really makes me so happy. And there's still time to do that. And if I'm going to see you guys again in 204 next semester, which I hope I do, come by and visit. It's like really, it puts a glide in my stride and a dip in my hip, and it helps me head off to the mothership. And except it doesn't help my board, which fail. Okay, but we're gonna start. Here's the deal. Very quick. Wait, sorry, I'm just trying to get the board back up. I don't know why the board's been doing this. This is really. Are you? Wait, so interesting. Sorry. Okay, I'm trying to do the board. Here's the deal. I will be. What? I'm just. Are you? What? Oh, this is. Yeah. Oh, well, now I see what my meeting room looks like. My waiting room looks like. That's what the waiting room looks like? Oh my God. Okay, whatever. So hopefully this will work. My board is entering as a guest, which is like fascinating. Oh, now I see what it's like to be you guys. Oh, it's terrible. I wouldn't want to be you. Oh my God. And then you have to have exams and get grades too. Oh my God. No, okay, hold on. I'm trying to. This is so weird. Okay. We'll see if this works. So here's the deal, and I hope you're here. I'm actually going to say this because it's kind of important. I'm going to say a bunch of things that are kind of important. Just give me an electronic signal if you can hear me right now, and like if you're tuned in, because these are like, okay, great. Thank you. Awesome. Thank you, David. Thank you, Caroline. Thank you, Colin. Thank you, Jamila. Thank you, everybody. Okay, good enough for me. Okay, so we have class today. We're going to do material. We have one more class on Monday. And also, if anything I say is wrong or confusing, stop me or put in the chat. And everything I'm about to say will be posted in Google Classroom to be explicit. But we have today. We have class on Monday. approximately 8 p.m. or so tomorrow night, or by around tomorrow night. It's not a firm and fast promise, but somewhere around tomorrow night, I will post a practice exam for your final exam. I'm going to tell you some things about it right now, but I'm going to post a practice exam for your final. I'm going to try for tomorrow night. If I can't get it out, I'll send a posting saying that and apologizing, then it'll be out Friday. But I'm going to try to get it out tomorrow night. Some of you will be able to work on it during the weekend. Some of you won't. Obviously, you're not meant to hand it in or anything like that. It's for practice. It's a rough draft of the final exam. So, it's preview, whatever. Most of Monday's class, I will address it. Like, I'll either give you partial solutions, or I will have posted partial solutions, and I'll answer questions about it and stuff like that. But like our last class, more or less, we'll be talking through the practice final exam that you'll have in advance. Again, hopefully that'll be to your benefit, whether you've gotten a chance to look through it before then or not. I'm going to tell you in a second largely what's on it, but it'll be hopefully shorter than the last exam. There will be some things on it that I will address for the first and last time, like in the next 2 days. Like, there'll be some material that if I gave it to you right now, you wouldn't necessarily know how to do it until you're done with today and Monday. Things about those equations, anything that's new, any new equations from today or Monday, the questions I ask will be very, very straightforward and not like ornate or complex or whatever, but there's just a couple of last equations I want you to have before you go into Physics 204. But anything that's on your final exam will be in this practice document that I'll give you tomorrow night, or at worst Friday, okay? Just like last time. And then any questions you have about it at all, of course, you can ask me during class Monday. The actual final exam will be posted on, okay, I got to get these dates straight. Will be posted approximately Wednesday of next week. So that's Wednesday sorry. Oh, I'm looking at the direct chat. Sorry. Oh my God. No, that's a great topic. Wait, there's a question in the direct chat. That's a great topic. Well, thank you. Let me address, and I will address it. Give me 1 second before I get myself distracted, but thank you for reminding me of that. The final exam, but remind me if I don't, thank you, direct chat person. I will address that in 2 seconds. Remind me if I forget. The final exam will be posted approximately Wednesday, a week from today, the 14th. And then I believe then exam period ends on you'll basically have, and then you'll have like till Monday of next week to do it. Okay, again, I'll put this all in Google Classroom to be explicit, but just to give you a sense of what's going on. So the next 2 days are us wrapping up and doing any final things. Basically, everything we do in the next 2 days is all in preparation for your final exam. I'm not intending to make your final exam some crazy thing. I'm intending to make it smaller. The final exam is explicitly only on this material that we've been doing since the midterm. It's not explicitly cumulative. So that's the story. Okay, and it's take home, all the same rules as last time, all of that. And during this time up until that, like, still it's the case, anything that you still want to catch up on, any places where you still find that you could still get yourself points, with one exception, I'll tell you, you could still submit to me and I'll still take them. Similarly, I have to get back a lot of points to a lot of you. Know that any work that you ever gave me is worth points, even if you haven't seen the points yet. There's any points that are adding up that still have to like turn back to you are all just positive points. Like, don't, like, they're not percentages, they're all just points. So know that. So I have to do some catching up. Some of you might feel that you want to do some catching up. That's all fine. Certainly up until next Monday. The only thing I don't want from people is the game turns. The nightly game turns. Don't give me a backlog of those, please. Like, don't start turning in like from September and October what you did daily in each class. That's pointless, kind of, weird at this point. but anything else is fair game. Any of the special games, even the ones that technically said they were due December 1st, like last week, that was just to say they're due at the end of the semester. You could still turn those in. Anything about video or avatar or YouTube or anything like that, fine. And again, just trust, even if you haven't gotten the points back, if you turn it in and Google Classroom acknowledges it, that means you're getting points, and the points will be included in your final average. So I want to, is that basically clear what I'm saying? Can you raise your electronic hands if what I'm basically saying as like the basic okay, great, awesome, thank you. Okay, now there's a question in the direct chat. That's a very welcome question, something I always forget to talk about, even though I'm on the committee and everything. Like, yes, there's this whole thing of teacher evaluations. I'm so sorry. There's this whole thing, which I really would, we don't take class time to do them anymore. But the whole thing of student evaluations of faculty, I could go on forever about this. The college takes them really seriously, far more seriously than you might think, or far more seriously than you might know. Like, we really do actually care. Obviously, they're painful to read. It's like, whatever, like they can be painful to read and stuff like that. But believe me, the college takes your input far more seriously and increasingly seriously. Like, I'm actually on the committee that works hard every semester to change the form, to update, to improve the form, to make it, believe me, the form gets a lot of attention, and your input matters much more than you might know. So please do. So someone just reminded me, those student evaluations of faculty that you're encouraged to fill in on your own time, or that, please do fill them in. I mean, it's an awkward thing for me to say, but obviously, whether you have positive experience or negative experience, I will never know. I never see yours personally, but I see all the results and all of that, and we all do. Please do fill them in. Thank you for reminding me. I mean, it really does make a difference. And the more people fill them in, the more it really makes a difference too. But so then someone just asked, are you supposed to fill them out separately for lecture and recitation? Here's the most yes, please. I know it's weird. You could put out the exact same thing for both. There is no difference between the lecture component and the recitation component of this course. I might have mentioned that before. That's like a weird registration, old historical. We don't do a separate recitation, as you know, and it's the same professor and all that. But actually, if you could fill them both in, even if you say the exact same things, that would be great, for a variety of reasons, but just because otherwise it looks like a whole, I mean, it's still fine if you don't. It's all your choice. But if you're actually asking, yes, to be honest, any form that you get, even if it's on the same person, it does make a difference to have all the piles be as filled out as they can be. And so please do, I guess, is my answer. I mean, if you can. Okay. Okay. Thank you, Nicholas. Awesome. Okay. And hello, Savannah. Good to see you. And hello, Elda. Okay. All right. So again, the details about the final exam, I'll post in Google Classroom, but just be aware that I'm going to post a practice for it by the end of this week. That's what we're going to, and I'm going to tell you in a way today, like basically what's on it. It's not going to be a surprise or something. And you'll take it home and do it and stuff like that. Also, I'll just say this quickly too, because I know people are concerned and stuff. I regard the final exam also as just another opportunity for people to improve or to get better at taking physics tests or to improve their grade. I don't mean the final exam. If you think you're doing well in the course, like, you still should study and take the final exam, obviously. But if you're go into the final exam viewing it as an opportunity to do even better, honestly. Don't go into it thinking, wait, I think I'm okay now, but if I blow this exam, I'm going to blow everything. Your ultimate grade in this class is far more determined by the best work that you ever do than you realize. It's not determined by your middle work. It's a complicated averaging system that is designed to favor your best work. Sometimes the averaging system does that even more explicitly than other times. But what I'm saying is, should I say this? There have been times even when I've decided at the end to put slightly more mathematical weight on whichever of the two exams a person did better on. I'm not promising that I'm doing that this time. I have to see. But I would never do the opposite. I would never do something to disadvantage any student. Sometimes, and I can't throw away an exam. I can't do that for a variety of reasons. I won't do that for a variety of reasons. But sometimes I will even go into the end and put slightly higher weight on whichever of the two exams. So in other words, it's different weight for each student. Go into this exam assuming that even if I don't explicitly mathematically do that, it's still psychologically what's going on. Whichever exam you do better on is going to have a far more of an impact on your overall grade and on my understanding of you than whichever exam you do worse on. Okay. So those of you who need to improve, please try to rock this final exam. And those of you who think you're okay, don't be afraid that it's going to mess you up. If you already have a good foundation in this class, I don't want to see that undone any more than you do. Okay. And I also want everybody to go into Physics 204 kind of like with a good attitude and stuff like that. So just know that. Okay. Okay. Oh, okay. And I'm looking. Oh, wait. Oh, okay. I'm looking. Oh, okay. Oh, cool. Thank you. Okay. All right. So we're going to go now. There's a couple of final forces I've discussed, but I'm going to explicitly discuss the final now for a minute. I'm going to give you an overview of what's going on the final. Like this is the soft overview. To know explicitly what's on the final, you'll see the practice exam. Okay, but okay. Oh, sorry. There's a hand. I'm sorry. Is that a hand, Amy? Wait. Sorry. There's also something in the Amy. I'm sorry. Do you have a question, or was that just from before? That's from
Yeah,
before.
it was from before. It was from before. Sorry.
All right, no, but thank you. Okay, cool, no problem. And then wait, there's something else in the direct chat from wait, is it? Oh yeah, of course. Yes, direct chat person. If you already didn't, I mean, yes, please, direct chat person. If you're seeing me, I can't see. Yeah, please do direct chat person. Thank you. Okay, cool. Oh, you guys are so great. I'm gonna hopefully never miss you because I'll keep having you. Okay. So I'm going to tell you right now, and again, you're going to see this explicitly in the thing, but I want to give you an overview. What it says in English here, it says notice I'm saying one problem. I'm not saying, I don't know if it's going to be problem number 1 or problem number 2 or what. And I don't know if you're going to have choices or what. Like, I'm going to try to keep this thing short, but one problem you're definitely going to have to do is much like this is like lab 5, which I know was a while ago, but I know how hard you worked on it. And I really kind of want to make your work on lab 5 worth it and have come to something. So because it is like a deep thing. So one problem will have you basically have you do what we've been doing the last 3 days in lecture. You're going to walk through system schema, pure free body diagram, Newton's third law pairs, action reaction pairs. And finally, choosing axes and doing a component free body diagram so that you can solve for the acceleration down a rough inclined plane and compare that to the acceleration up an inclined plane. Okay, and I'm gonna write those results for you in 1 second. But like I'm gonna want you to walk through to some extent the process for solving for the acceleration down a rough inclined plane and comparing it to the acceleration up an inclined plane. And your goal when you practice this problem or when you think about it, when you go back over class notes, your goal is, yes, can you do all the diagrams? And yes, can you do all the equations and stuff? But ultimately, can you step back and can you really see and express, like in English, can you really see why the accelerations are different up versus down? And why in particular, in fact, the acceleration down is actually lower in magnitude than the acceleration up, and why therefore that means, and this was the conclusion of lab 5, like the conclusion of lab 5 that we found ultimately was that if you flick something up, a random, realistic, arbitrary sliding object up a random but like low angle, long, rough inclined plane, what you found, I believe, in lab 5 is that if you flick something up and it goes up the plane and then just naturally, runs out of steam and comes back down the plane, what I think you ultimately found in lab 5 is that it takes less time to go up and more time to come back down. That was the conclusion in lab 5. And if you were following along and really being a physicist, well, first of all, I think many of us, certainly me, would have never predicted that. I think in lab 5, you were even asked to make a prediction at the beginning. And I know for me personally, if I were honestly asked, if I were asked, you flick something up, it goes up, it comes back down. In reality, something goes up and then it comes down. If someone asked me to predict, like, what do you think? Is it going to take longer going up or longer going down or whatever? As just a person, as a human being, like before taking a whole bunch of physics classes or whatever, I would actually probably guess that it takes more time to go up than it takes to come down. I think that's a fairly natural, reasonable, common guess that things have a harder time going up than they do coming down. So I would have guessed that the thing would take more time to go up than to come down. Then I'll even say, if I had taken a bunch of physics, sort of, or some physics, or I was getting used to physics classes and science classes, and I knew some things, and I knew that sometimes physics is like a surprise or it's tricky, or even if I knew certain things about gravity and all the kinematics from the first part of the semester, to be honest, what I might have said is, oh, I know the acceleration due to gravity is always the same, whether you're going up or you're going down, which is true. Right, and if you're going straight up and down, it's like 9.8. If you're on an inclined plane, I might have known enough to know it might be less than 9.8. It might be like 9.8 times the sine of the angle or something. I might have known that, but I would still be thinking like, all right, but it's the same acceleration. It's the same gravity, whether you're going up or going down. And I know that like when things are thrown in the air and they come back down, they always take the same amount of time to go up as to come down, right? And I might have even thought, oh, but now there's friction. Isn't friction going to do something? But then I would think to myself, but it's the same friction. It's the same surface, whether you're going up or going down. So to be super honest, all of you, and I'm not trying to confuse you right now. I'm trying to clarify something that is, I think, confusing. If I were even a physics student and someone asked me, hey, you flick something up and then it comes down on a rough inclined plane, how do you think the times are going to compare? If I didn't just go with my gut instinct that things should have an easier time coming down than going up, I might have thought about it kind of with my physics hat. And I probably would have ultimately said, well, this is a physics thing. So I guess the gravity is the same in both cases and the friction's the same. So I guess they take the same amount of time. Honestly, not only is that what I would have said, I think that is what I said when I first thought about this. Now, I want to be clear to all of you that the reason we spent so much time on that lab and so much time now talking about it like weeks later in lecture is that the reality is that that's not what happens. Either in theory on paper, or even in the reality, if you take sort of good data and you're sort of careful about it, in the reality of an actual like lab, that what I want you to know first and foremost is, in fact, the object takes more time to come down than it does to go up. That is the conclusion of Lab 5, that if the conditions are not, if the conditions are fictional or theoretical or idealized, if the conditions are just good and controlled, things go up quickly on rough inclined planes and they come down slowly. First of all, I want everybody to know that. Second of all, and I think it is a surprise, if you found that totally obvious, if you didn't even have one moment being surprised or confused, then I think you're very confused. To be like, if you for 1 minute you should think it's a little bit surprising or a little bit confusing that we are saying things go up quickly and then they come down slowly. Now the goal, your goal on the final exam, on one of the problems of the final exam, is to work through enough of the physics to actually show that while that, even though that is a surprise, it totally makes sense and has to be that way. Okay, I think it's a worthwhile physics problem because I think physics does its best job when it shows us things that we wouldn't have thought or didn't already know, but that once we see them and think them through, really do make sense. Like that's when physics is really doing its job. Whether it's showing you about black holes or big bangs or all these crazy things in the universe, people take them seriously because they are surprising enough to be interesting, but it turns out that they're logical and rational enough to be convincing. That's when physics is cool, I think. So what am I getting at with this final exam problem? If you do the diagrams and you, just like we were walking through yesterday and the day before in class, if you do the system schema and come from that, the pure free body diagram, and then you choose your axes appropriately, so I'm going to remind you now of the result of this. Aha, what just happened? Okay. Okay, so I'm not going to read you all the work right now, the work from yesterday, Monday and last Wednesday. But if you look through all that work in the class notes, where we tilted our coordinate system and we did the pure free body diagram, then we divided up the diagram into components. If you look back at all that, what you ultimately find is when we're accelerating down the plane, We have a component of gravity that's pulling us down the plane. Sorry. I just did it again. Sorry. See, I'm even doing it. Okay. When we're coming down the plane, gravity is pulling us down the plane, but friction is going against our motion, going up the plane. The component of gravity is g sine theta. And again, this part is what we got all from Wednesday. But in other words, there's gravity pulling us down the plane, but while we're sliding down the plane, friction is pushing against us up the plane. So they're in opposite directions in that diagram, if you looked Wednesday. Whereas if we're sliding up the plane, gravity is still pointing down, but friction is now also pointing down if we're sliding up the plane. So you can't see these equations until you do all that other work. But once you do all that other work, and if you're in this coordinate system that I mentioned yesterday, the tilted coordinate system, then you find that the acceleration when you're going up the plane or down the plane differs just by this minus or plus sign in the middle. And that minus or plus sign makes all the difference in the world. What we're basically saying is, what we are saying is that when you're sliding down the plane, all the forces are working against you, but they're all working together. When you're sliding down, sorry, I keep saying that. Oh my God. When you're sliding up the plane, all the forces are working against you. Yes, if you're going up the plane, gravity's against you, friction's against you. So you might think that that would make you go really slowly. In fact, everybody does tend to think that. But the two forces are working together with each other. Friction and gravity are both pointing in the same direction. So they make a huge net force. Magnitude-wise, the force against you is huge. It's against your direction of motion, but it's huge. F net equals ma. So when you're on your way up, the magnitude of acceleration is huge because the net force is against, which is against you, is huge because all the forces are reinforcing each other, acting together in the same direction. So when you're on the way up the plane, you've got this enormous acceleration value. And you like it's some number plus some other number. Say the numbers are 3 and 4, then it's like 3 plus 4, 7. You might say to yourself, but wait, it's an enormous value, sure, but it's like against me. Like it's like negative, isn't it? Like I'm going up, but it's pointing down. Yes, you're correct. It's an enormous negative acceleration. What does that mean in English? It means you're slowing down, right? It means that when you're on your way up the plane, you are losing velocity at an incredibly rapid rate, right? And when are you going to get to the top of the plane? When you run out of velocity. When you hit zero velocity, you'll stop, right? So on the way up the plane, you're losing velocity very rapidly. And as soon as you're out of velocity, you're done. You've gotten to the top. Like that's your top. It's you run out. Now you start coming back down the plane. The two forces aren't working together anymore. Gravity is pulling you down. Friction is going against you. You might think, well, now at least I'm getting help from gravity. So now won't I go faster or something? But here's the thing. The two forces are not working together anymore. The same gravity, it is the same gravity force as before, and it is the same friction force as before. But friction is flipped direction. So it's not helping gravity anymore. It's in conflict with gravity. So let's say those two numbers were 4 and 3, right? Let's just say like the AG sine theta was 4. And I mean, the G sine theta, and say the mu G cosine theta was the number 3. When you were on your way up, they added together and made 7. Now you're on your way down. They're in conflict. They're subtracting. It's no longer 4 plus 3. It's now 4 minus 3, 1. I'm just making up numbers, but just to make a point. So on your way down now, you have a much smaller net force on you. because the forces weren't working together. You therefore have a much smaller acceleration on the way down. Are you speeding up on the way down? Yes. I mean, it is now an acceleration that's in a favorable direction, you might say. But what we're saying ultimately is, on the way back down, your acceleration means the rate at which you're gaining velocity. So on the way back down, you do not gain back velocity at the same rate that you were losing it on the way up. So on the way up, you lose your velocity really rapidly, and boom, you run out of velocity, you're done, you're at the top. So you went from a velocity of, let's say, 15 meters per second to 0 meters per second really quickly. Now you're at 0 meters per second, you start coming back down, you're gaining back that velocity, but you're gaining it really slowly. You're like 1, 2, 3. So by the time you get all the way back down to the bottom of the plane, you don't get back all the way up to 15. You don't have time or distance to get back up to what you started with. You gain back more slowly than you were originally losing velocity. So if on the way up, you were going from like 15 to 0, that's an average velocity of 7.5 meters per second. I'm just making up numbers, but to make a point. On the way back down, you gain from 0, not all the way to 15. You'll just gain from 0 to like 10 or something, because you're gaining back more slowly than you were losing in the first place. So on the way back down, say you go from 0 to 12 meters per second rather than 15. Then your average velocity on the way back down is only 6. Like 0 plus 12 divided by 2 is 6, rather than 0 plus 15 divided by 2 is 7.5. So on the way back down, your acceleration magnitude is smaller than your acceleration magnitude was on the way up. And therefore, ultimately, your average velocity on the way back down is smaller than it was on the way back up. So you will take more time to come back down the same distance than you did to go up that distance. The block should go up more quickly than it comes down. And the reason is this whole proof that, okay, what I'm saying is there is going to be a problem on the final exam where you have to sort of walk through this, much like Lab 5. If you feel like you totally understood Lab 5 while you were doing it or you rocked it, good, then you have a huge advantage going in. But if you always felt like Lab 5 was fuzzy, you kind of want to get it straight now. Lab 5 is meant to be a surprise. We don't think it's obvious. We don't think that you would walk in expecting that things take more time to come down than to go up, but they do, and that's what you're proving here. So if you had a little bit of confusion, it means you are thinking properly, but you want to work through that confusion and look through the diagrams and look through the force components and see that basically all the forces are the same on the way up as on the way down, except on the way up, they're adding together. And on the way down, they're in conflict with each other, all because friction flips direction and gravity does not. That's the bottom line. Okay, so you'll know your goal, and I'm going to move on in 1 second. I'm going to move on. But one of the problems in the final exam is you need to know the diagrams, the equations. You need to see, you need to be comfortable with what I just wrote here, but you need to understand it in English. I don't know how I'm going to ask it yet, but you're going to be prepared to show me really that you can explain this conceptually. Don't just memorize the equations. Okay, so that's one. So one question is faster up, slower down, Lab 5, however you want to. Okay. Now, that, in order to show that, in order to get those results that I just put here to compare, you have to be in the tilted coordinate system to see this. It is much harder to see this if you're not in a tilt. In other words, you've got to break up gravity. Yeah, you've got to break up gravity into mg sine, mg cosine. But another question that's also on the final exam that we've been alluding to yesterday, let me just change that. Sorry. Okay, on the other, another question on the final exam, very related, also about these inclined planes, because inclined planes combine all vectors, forces, all the laws. So in another question, I want you to see what we've been doing for the last couple of days. Another thread of this same topic is that the choice of coordinate system matters, that no matter what choice you make, you'll get the same answer, but you'll take different computational processes to get to that answer. So and for this one, since you would have already done a lot of work with friction, all that on the other question, on this question, when you compare the two coordinate systems, like I've been doing for the last couple of days, for this one on the final exam, I'm going to tell you right now, you're not going to have to worry about friction for this one. You'll worry about friction for the question I just described. For this question, you won't worry about friction. But so in short, what I'm saying is this. With this problem, with a block sliding down a smooth inclined plane, for this one it'll be smooth, no friction, okay, but again, an inclined plane, your ultimate goal here is to show, to work out the physics, to solve for acceleration. You're going to solve for acceleration. You're going to do it two different ways. One way, you're going to choose a standard coordinate system that's parallel to the lab, where the x-axis is parallel to the horizon and where the y-axis is parallel to the wall. And you're going to do the physics in that coordinate system and solve for the acceleration. Then you're going to redo the physics. You're going to make the other choice where you tilt the coordinate system and line it up with the inclined plane itself, with the direction of acceleration. In either way, you do it, you're going to get an answer that I'm telling you right now. The answer is A equals G times sine of theta. That the acceleration along the plane is some percentage, some fraction of 9.8. The bigger the angle, the bigger that fraction. By the way, I hope that's beginning to make some sense to many of you. Like that, when I say A equals G sine theta on a smooth inclined plane, what that... Right, if you remember that sine of an angle is just some fraction that ranges from 0 to 1. Think of it as like a percentage that ranges from 0% to 100%, right? To say that the acceleration of a block on an inclined plane is G times the sine of theta, is like saying the acceleration on an inclined plane is some percentage of 9.8. If the plane is purely horizontal, if the angle is 0, then the block doesn't accelerate at all. It accelerates at 0% of 9.8. As the plane gets steeper and steeper, as the angle gets bigger and bigger, the sine of the angle gets bigger and bigger. It's a bigger and bigger fraction. So the overall acceleration becomes a bigger and bigger fraction of 9.8. So like if the angle's 30 degrees, the acceleration along that plane is like 4.9 meters per second squared. If the angle is 45 degrees, the acceleration then is like 6.9 meters per second squared. If the angle is 60 degrees, then it's like 8.5 meters per second squared. And when you get all the way up to 90 degrees, where the angle is 90 degrees, the sine of 90 is 1. So it's 1 times 9.8, 100% of 9.8. That's all that means, right? G sine theta means a percentage of G that is based on how steep the angle is. Kind of makes sense, I think, or I hope you'll see by the final exam that that makes sense. Well, I'm here to say that you can get that result either way, whether you do the physics in this coordinate, in the obvious natural coordinate system of just looking at the inclined plane and dividing up the forces, or if you tilt your head to line it up, to line the x-axis up with the inclined plane, either way, the physics will get the same result. But the truth is, one way is more natural and obvious, and everybody would do it if they didn't know about this option. But the other is a much faster mathematical calculation, and that's what I want you to work through and show on the final exam. Again, and I've shown you a lot of it already, or actually I've shown you more than is necessary the last couple of weeks. But the whole difference in the two coordinate systems, they don't produce a different system schema. They don't produce a different pure free body diagram. It all has to do with the way that you divide up the vectors. So I'm going to give you one more like piece of hint or knowledge on this before I'm looking at the time. Yeah, what I'm saying is, okay, either way, no matter what, this is the pure free body. The system schema is this. Sorry. Either way, the system schema is the same, and the pure free body diagram is the same. The weight of the Earth pulls down on the block. The normal force of the plane pushes the block to an angle. Either way, that's the same. The question is how you divide up the forces into components. The question is which one you divide up, mg or n. And what I'm saying is, in one case, if you don't tip, so sorry, what I just wrote there was the distinction is, okay, so I'm going to just show you, and I'm not going to do the whole thing now. I feel like I've been doing it for the last 3 days, but just to highlight what I'm getting at. If you don't tilt your head, if you keep your coordinate system aligned with the lab room, then normal force is what has to get broken up. So you do something like this. But if you do tilt your head, you get something like this. And from those, that makes this all the difference in the world. Either way, you're going to then do F net equals MA, and you're going to divide F net equals MA into an x-axis statement and a y-axis statement. But in the top diagram, the x-axis statement has to do with n sine theta, and the y-axis statement is n cosine theta minus mg, or mg minus n cosine theta. And in the other one, The y-axis statement has to do with n, and n minus mg cosine theta, and the x-axis statement has to do with mg sine theta. So you're going to do out all the math either way and solve for a. You will see that you'll know you've done this right if you get the same a answer for both. Sorry, you'll get the same answer ultimately for both, but you're going to do a lot more work in the top one, frankly, than in the bottom one. The top one is less natural, but will lead to a lot more work. And the bottom one is, the top one is more natural, but leads to a lot more work. The bottom one is less natural, but leads to a lot less work. And that's what I want you to be able to understand. Again, this is the problem where you need to do a bunch of stuff, but you need to be able to stand back and look at what the big picture is. The big picture here is both methods equivalently get the same correct answer, but one method is less instinctive and a lot more computational. And the other method, one method is more instinctive and a lot more computational, and the other is less instinctive and more computational. And that's why we have to make these choices in physics. Okay, so that's another problem in the final exam. Now, the last problem, the last one I'm going to tell you about. Okay. We have like 22 minutes. I'm going to give you some last few equations that we've never discussed yet in the lecture. I'm going to give you in the last 2 days. You're going to be asked about them in a very sort of primitive way on the final exam. I'm telling you now what you need to know and what you'd be asked about. We've been dealing with all these forces. We have the force of friction. We have the force of tension. We have the normal force. We have the gravitational force. I wanted to say some things about two final forces before the semester's over. One force is the force that's exerted by a spring. If a spring, because you're going to deal with a lot of this, like for a number of weeks at the beginning of Physics 204. So it's good to know about it before you get there. Let's say we have a wall and we have a spring, a horizontal, like a coil of metal attached to the wall on one end, and on the other end, it's attached to some mass sitting there, okay? The question is, how does a spring work? Like a spring certainly touches the mass at the edge of it, and springs pull and push on masses. You know from life experience, the way a spring works, the whole point of an elastic bit of material is if I pull the mass to the right, the spring exerts a force and pulls it to the left toward the wall. If I push the spring in, the spring pushes back and tries to adjust it. Ultimately, with a spring, you know, if you're not doing anything to it, the mass will sit at the edge at some stable, seemingly comfortable, preferred location. We call that location the equilibrium location. And we usually designate it as position x equals 0. Like x equals 0 on a spring is where the edge of the spring would be if we are not doing anything to it. And the place where the spring in the real world generally eventually ends up in if we let it go long enough. So the equilibrium position of a spring is just that, is the position, is the relaxed. And it's the place where if you put a mass there and give it zero velocity, if you just put a mass at the equilibrium position on a spring and you give it zero velocity, it has no reason to do anything. It won't change its velocity at all. It'll sit there forever if you put it there, right? And it'll maintain an acceleration of zero. Put another way, right? I mean, that's what the equilibrium position by definition means, place where acceleration is zero. Where if something's not moving, it has no reason to change that fact. So if acceleration is zero at an equilibrium position, another way of saying that is that's where the net force is zero. But other places, if you put the mass any other place, like right now, this mass is at position, let's call it x equals x naught. It's at some position, some, let's call positive to the right. I mean, let's call it to the right positive, let's call it to the left negative. If I put this mass, if I hold this mass somewhere to the right of the equilibrium position, I know that if I let it go from there, the spring is going to yank on it and pull it back toward the equilibrium. And if I push the mass all the way to the left side of equilibrium and I let it go, the spring is going to push it out toward equilibrium. Springs always seem to be trying to restore their edges toward the equilibrium position. Springs, in other words, exert forces. And the forces always seem to be trying to get masses toward the equilibrium position. I'm going to go one step further and say, when x equals zero, when the mass is at the equilibrium position, the spring does not exert any force on it at all. That's why we call it equilibrium. It's stable there. It's unforced. It's unaccelerated. It's happy. When the mass gets a little bit away from equilibrium, the spring starts to exert a force on it. It seems like when we go from zero position to some position, the force exerted by the spring goes from zero force to some force. That pattern continues for a while. That is to say, it is a pattern. It's not just a jump. What I'm saying is that if you bring the mass to any position x, where x means some amount of meters away from the equilibrium position, if you bring the mass to any position away from equilibrium, the spring will exert a force on that mass to bring it back to equilibrium. And it is a pattern. It's a relationship. It turns out, apparently, the farther you bring the mass from equilibrium, the harder the spring will fight to bring it back. I'm telling you that. That's something that, in order to really know that for confidently, you'd have to test it out in the lab. But I'm starting by saying we know that if there's 0x, then there's 0f. And if x is bigger than 0, then f gets bigger than 0. This goes on and on. It is actually a proportionality. It's a relationship. The bigger the x, the bigger the spring. In fact, that's why we use spring. That's why springs are spring. That is what it means to be springy. Why gym equipment and stuff uses springs. What we like about springs is and why springs are used for things that we want to adjust to different people's amount of different strengths, and we use them to build people's strengths, is because if you have two masses that are connected together with a spring, to hold them here is hard, but to hold them way out here is even harder, right? And to hold them out here is even harder. The more you stretch a spring, the greater force it exerts to restore that spring to equilibrium. The force is proportional to the displacement. I'm going to fill in this graph now. I'm going to say, but if you're with me so far, the force goes up in magnitude as the displacement goes up. But two things. One, it goes up in magnitude, but direction-wise, it's always directed oppositely to the displacement. Like if you pull the mass out here to the right, the spring does pull to the left to try and get the mass back to equilibrium. If you put the mass on the left side of equilibrium in the negative numbers, the spring pulls to the right with a positive force to get it back to equilibrium. So the force is always directed oppositely to the displacement. That's number one. I'm sorry. So if I were to make a graph of what the force is doing as a function of displacement, the graph would look like this. It would be a straight line, but it'd be in the fourth quadrant or in the negative quadrant because it would be negative in other words, it would look like this. Straight line that gets bigger and bigger as x gets bigger and bigger, but it gets bigger and bigger negatively because the force is always directed the opposite direction from displacement. The slope of this line is constant. I mean, because it's a straight line, right? It's like y equals ms plus b, but b is 0. M is some constant. M the slope of that line, the rise per the run, right? The rise per the run is called K. And K is how stiff the spring is. How strong the spring is. The bigger the K, the more newtons of force the bigger the K, the more newtons of force is exerted by the spring for every 1 meter of displacement. In other words, the summary of all of this any springs exert a force. Oh no, I just lost the board. Hold on. Okay, this thing written at the bottom of this equation is called Hooke's law. It says that for any spring of some stiffness K, the spring will exert a force that is opposite in direction, but directly proportional to the displacement from equilibrium of that spring. So K could be a number like 200 newtons per meter. A spring of 200 newtons per meter is stiffer and stronger than a K of 50 newtons per meter, because a K of 200 newtons per meter means for every meter that you stretch out the edge of the spring from equilibrium, the spring is exerting a force of 200 newtons. So if you stretch it out like 7 meters, then the spring is exerting a force of 1,400 newtons. Springs exert, so this is what elasticity means. An elastic force exerts a force that is directly proportional to displacement, but in the opposite direction. And the constant of proportionality is called K. K refers to the stiffness of the spring. This is just something I want you to know. You'll see in the practical exam, we're all going to give you like a simple, straightforward, not crazy problem that asks you to do sort of some plug and chug or something with this. Okay, but this is a force. This is another force like friction or like tension or like the normal force or like the mg force. It's another force that goes into the left side of F net equals ma. when we're solving Newton's law problems. Okay. There's one last thing. We have 10 minutes. So again, I want you to know that it is in the document. It will be in the document, but we're not going to make a big deal of it. We're not going to ask a million things about it. But just I want you to know that. So that's part A, right? Yes, that's part A, and here's part B. I'm going to give you part B now of the other problem, and then there probably is a part C, which will be the last thing that I will say, or the last thing that I'll do in our very last class on Monday. It's also not a big deal. It's one other equation, but I'm going to give you the part B right now. Okay, I want you to notice, and I'm watching the clock, I have 7 minutes. I want you to notice one reason this elastic force, the spring force, the Hooke's law force, F equals negative kx, is worth knowing, first of all, because springs are in a lot of things in the physical world. Elasticity is a big part of the physical world, but also because it's the first force we're seeing in our study of physics where the actual amount of the force depends on where the object is. Our other forces don't really do that. Mg, the force of mg, it's the same whether you're here or here or here. It's just the number. Mg, it's a constant force. Tension, same thing. It's a constant force. Even friction. But this one seems to be a force that gets stronger and stronger as you get farther and farther away from some place. How do we deal with that in physics? It raises a question. How do we deal with forces that actually change as a function of position? The way we deal with forces that change as a function of position is we introduce one final idea that I'm just introducing here briefly. You actually thought about it a lot in lab 6. We're not going to have a whole test about lab 6 or anything like that, but I want to bring some material together. So I want you to know that the way in order. Okay. The thing we're ending on today, we've got like 4 minutes. We're going to define, and again, you sort of saw this in lab 6, but I'm saying, as far as I'm concerned, I'm saying this now for the first time. I'm not assuming that you understand anything that other than what I'm about to say, but we define, in order to deal with forces that change in value as you move from point in space to point in space, in order to deal with forces that change in value as we move from point in space to point in space, we construct or invent or define or imagine this idea called work. We define work, W, work to be force times displacement. Okay, again, if all forces in the world were always constant and never changed from place to place, we really wouldn't have much use for this idea. But since there are forces in the world that change from place to place, we step back and we look at forces act throughout an interval of space. We start looking at the accumulated effect or consequence or impact of what a force does as it continuously pushes or pulls an object throughout an interval or a region of space. And we define, this is a definition, it's not a discovery or anything like that, but we say work equals force times displacement. Now, the one thing is I put little deltas here, and this is where I'm going to end with this. I put little deltas before the W and before the X that connote like delta as in difference, as in like delta Y means rise, like Y2 minus Y1. So delta means difference. I put, and it usually connotes a small but finite difference in two values of a variable. I'm putting the little deltas there just to connote that, strictly speaking, and we're going to end on this for right now, so don't, but strictly speaking, the definition of work is force times displacement, as long as you're talking about a small enough displacement for us to be able to know what the force is. Like work equals force times displacement works best as a definition if you have an actual number to plug in for F. If displacements start getting too large and the F starts changing too much, we don't know what to plug in for F, so we have to do something a little bit more exotic to this. But the basic idea that I just want to leave you with today, the basic two ideas that are good, there's going to be some questions about that are going to be like less involved than the other questions, but you're going to see some question in the practice document about F equals negative kx, that's the force being exerted by a spring, and you're going to see something about what work does the force do, the force of the spring do over some interval x. 1 joule of work is defined to be 1 Newton of force times 1 meter of displacement. Last warning, there may be a part C to this, which is what I'll discuss on Monday in our last class, but you'll see it in the practice document. So again, there'll be a little bit in this practice document that you won't have known until today and Monday, but there'll be nothing on your final exam that's not in this practice document. Anything that's in the practice document that's sort of new to this last week will be at a low level of inquiry. And you will get the practice document, and any questions you have about it and anything you want to talk about it is what we'll talk about on Monday. And you get back any stuff that you still need to get to me, and I will get stuff that I still need to get to you. And you've been very sweet and kind and smart. And so have a great weekend. Thank you.
Have a good
Thank
weekend.
you. Have a great day.
Have a good day, Professor.
Thank you very much.
Have a great day, Professor.
Thank you very much. I appreciate you too. Thank you. Thank you. Have a great day. Oh.
Hello, Professor.